Yeah, I call it.
Alright, so I guess it's being recorded now.
You might want to move the board up.
Yeah, I can see it. So
Okay.
no, it's fine. So in today's talk, I'll basically go through our recent paper, document number, yeah, this one, by Linus and ARK. So maybe I'll just summarize our result, which is result. I'll summarize the result first and then see how to try to clarify that. So our result is basically so yeah. So there are no new redefinitions. Uh, of prime figure or let me just write this one. Then as soon as no and then let me put 10 dimensions, but and not necessary. But yes. So I guess everyone can recognize my writing.
Yeah.
So that's the result. There are no field definitions that of a prime cubic for an SNS sector of low energy effective field theory in 10 dimensions, such that the reduced one, basically doing theta reduction on the torus, has a manifest ODD symmetry. So that's the meaning, but I hope like I'll clarify it. Yeah. But before doing that, let's go through some, some conventions and notations that we are sort of using. So, yeah. So string theory basically has, predicts some massive states, has some massless states, in which massive ones are typically of order 1/1 and upper prime basically straight lines squared. And in the massless sector, there are like something simple NSNS sector, which includes some metric field, which is two-fold field, and a scalar dilaton. And well, there are other fermions, are fluxes, but we don't care about that today. So that's the that I'm interested in today so far. So since this one typically people take still has to be Planckless sort of stuff. So these massive states are typically of like a Planck mass order stuff, which is very huge. So you can integrate them out and only do some low energy effective field theory that describes the dynamics of massless sector only. And that typically gives some effective function. Which can be organized in a double Higgs function. So that's the general structure of the effective field theory. I mean, here we can also include some R plus stuff, but we are only taking of NS and S, so, but there's no difference actually.
What is before the sum? Is this bar J?
This one?
Yeah, what that's.
Oh, that's the square root of minus.
Oh, it's the square root.
Yeah, my writings. Yeah, please ask me.
Yeah.
Well, yeah, my writings are good and I like to kind of buy. And also this is GS, which is this company. Well, roughly speaking, in this case is the exponential of the dilaton. But strictly speaking, it's the working interpretation of that. Anyway, it's in this case we only take care about zero case, so zero. So that's the action basically what we are considering today. No questions so far, right? So in general, like so one wants to like write down the explicit expression of this effective action. One can match by amplitudes by like from these ansatz, writing down the general ansatz and match the amplitude to the three amplitudes. Or like one can use some symmetry constraints, like it has to satisfy some sort of symmetry, and you can fix some terms. Or like one can use some duality symmetry, which is basically our case, like T-duality here. But I won't go through like how to really use that to fix the stuff, since that's taught like in the last theory, like 6 months ago by Vince. So, but still, like I'll review like some relevant notations that we use. All right, so that's the action, and we want to use sort of T-duality, or more strictly speaking, we want to use the fact that's shown by Schatzen and like well, first shown by Schatzen, but then revisited by Schatzen, Ohm, and Zwiebach. So the fact we want to use is that, so roughly speaking, so you can take the so we sort of take the calculator direction of torus, the dimension torus, so result in some d minus 1, d minus 10 minus 3 dimension. And this theory will have only symmetry up to what they originally showed like is basically having the S matrix elements as there is quality symmetry. So S matrix elements can be like there's some unity up to field resolutions that doesn't change your S matrix element. So that's why we allow some field resolutions there. Right? Anyway, our fact that we'll use is that this action once reduced on let's say dimension torus, but thinking we are not really taking care of the torus or not. We just want that our effective action has like a d coordinates be independent. But effectively, that's just the introduction towards the dimension towards. So yeah. Anyway. So that's the fact that we are use, and we're gonna see how this fact allows us to analyze like this action, like its properties, and it's like some of the terms can be like just fixed by using this fact. No questions?
So I guess you talk about eventually you want to get to alpha prime correction, right? So how far did home Spielberg and Sen do this to all or to alpha prime?
Yeah. So here this action is like
No all orders.
yeah,
But no orders in G string coming.
no, there's no genus correction for that. So okay, here we have.
But how does that square with the Russellian? Is the void manifest that is the void manifest? So this seems to sort of is that it maybe it looks like a contradiction of the conclusion you want to get to.
I'll try to clarify.
Yeah, what's the difference between the two?
So like, so there, I mean, that's the point of this talk, right? I want to clarify it. That's the.
Is the manifest what manifests are important?
So basically, I'm saying that if I have some theory in 10D, I do sort of this reduction numbers. I get some d minus, so 10 minus d dimensional theory. Like I cannot have, so this theory cannot be ODD like symmetry invariant, like without field redefinitions. I always need some field redefinitions to push. Okay, well, by order, like I need some field redefinitions to. Okay, so let's say if we stop at this order, alpha prime to the qubit. And I want this theory to be ODD symmetric. I always need to do some field redefinitions. That's the claim. And by manifest, I mean we don't need to do field redefinition. Okay. But yeah, like I mean, this talk is aimed to like clarify that, but I guess like I'll show you like more examples and see how the statement really makes sense. But yeah. So let's see how this part really works. So very roughly speaking, like for a metric. So let's say our coordinates can be split according to this Weilong. X and let's say that's y. So that's n dimension. And that's the rest of it. So that's the notation. Some index with the prime means something that's on board in the general index, and something with like a underline. That's just the original 10D field, like our coordinates. And roughly speaking, we have say and one. This one is sort of
Still, sorry, prime coordinates are the, with the T's, right?
Yeah, in the T.
Okay.
So very roughly speaking, for the NSNS field contents, if we take one index to be prime one, we'll get some. Okay, these are basically the KK vectors in the lower dimension. And one can combine these two into something that's so one just simply stuck them together and they will find out that okay, this stuff is only the vector. So you transform some into that. Oh, these are explained like 6 months ago. So I hope you remember. No, okay. Also, one can use same, I mean, larger than the sector, so which that everything is developed from the substance. So you could take two indexes to be internal. Then they somehow, okay, so they will like form some ODE matrix.
So the logic of the notation is that when you have an underscore on the matrix, that's because the object actually lives in the big space, but then the indices are m and n prime. That means that there is some now in the what's it called in down in the basis manifold, and then in the TP on the source. Because it is like the underline underscore means the big space, and
Okay, maybe
Yeah, right.
maybe maybe I sort of want to speak like this kind of notation, but since I thought that maybe you still remember something from 6 months ago, but
That's fine, right?
well,
So that's
Yeah,
fine.
it's-
Underline is the original, I think it's fine.
yeah, it is fine, but like because I don't want to like write down all the definitions. Then it takes like at least 10 minutes or 10 minutes to read. But the idea is that so let's see. So that's basically the two fields that we have like indices in here. And these are interpreted in the lower dimension. Something that's a metric, so metric, financial. And that's some KK vector because it has one index of some kind. And something like a scalar. Anyway, for this. Vector. Because we have this one, that's a matrix. Q form and metric. And my question now, this two, so they can group up into something like this. That's a ODD vector. And this two can be grouped up into something like a P times 3D matrix. That's what they call as generalized metric, but we don't really care about that so far. Anyway, the point is this stuff also transforms on the ODD, which is basically was it this way? Then for like there's a natural sort of invariant tensor ODD, which is something like this. Because by definition of ODD, so ODD is sort of defined as some metric in G with such that and then theta and the theta. So that's analog to Lorentz group kind of definition. So here using this general so ODD vector and this ODD matrix, we can like obtain two ODD scalars. By this cool. So if this transforms, the one in the middle is invariant, so it goes back, that doesn't transform. And this one, okay, well, there are some subtleties that I forgot now. If I remember correctly, it's basically OTOG, OTO. This one gives some minus, 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 plus, plus, plus. And that one also gives sort of minus, minus, plus, plus. So after all, they are basically identity. So they also be invariant. Okay. This part, it's like a heavyweight argument that I haven't really remember now. But basically, the take is that like this one and this one, they should be ODD scalars. So from these two ODD scalars, and we further assume that we can sort of assume GM to be zero. So this is the statement. Basically, we don't want to care about internal like scalar fields. It's sort of truncation. This will simplify like the matrix integers identity. So the following expressions will be very simple to write down, which is here we're basically saying like if you have A1, A2, these two expressions are scalars themselves. Now we can like using a different basis, or like instead of A1, A2, we can use A and A hat as defined as follows. And this one is basically now equivalent to the so these two independently be in the scalar terms now. So you can just say like you can verify this by simply like putting this expression into the product and then find out there's a like combination between this and there's scalars like 3 by 10. And so that's a scalar, that's also a scalar. But now only the duality in general. Something that's not scalar. So
What was the reason for taking H to be 1, 1?
So, I mean, so if you don't do this assumption, then that expression is gonna be very complicated. And
Yeah.
this won't, so this expression wouldn't be as simple as this. This is the same. So that's for simplicity.
Well, I like a world where I can choose everything to be such that it becomes beautiful. Sometimes it's not, because really A1 and A2 comes from the letter which looks like F, but maybe it's a G, I don't know. And B. Okay, so G and B, it comes from G and B. A1 and A2 comes from G and B. The other stuff in H also comes from G and B. But in H, you say, well, B is 0 and G is just 1, but you still
So
keep
there-
A1 and A2 non-trivial.
So first of all, like this, so they are different notation.
That's fine.
So these are
Sure,
scalars.
but they come from G and B in the upper.
Different sectors.
Yeah.
Sure, but why should, but this particular sector be trivial and this not? But I guess, or are you saying that if you turn on GMB everywhere, things will still be invariant? Although if you take it apart, it becomes messy, but you can still do this thing and define the two invariants, or right? Because this expression ATHA is still invariant, even if H is complicated.
Yeah. So that's true. So, okay, the main motivation for this is just for simplicity of calculation. So it's similar to like, so quickly reduction for, let's say, pure gravity. So we only have a metric in higher dimension on this one. This will give us some lower dimensional metric, some K vector, and some like a scalar. And in principle, if you have some KB ansatz there, you can just put in the ansatz and write down your, let's say, so original. So let's say, okay. So let's say original dimension is 10-dimensional.
I understand this completely. The only thing which is weird is that you're saying, let's say the metric on the base manifold or on the uncompactified space is trivial. There's no B field. The metric on the compactified manifold is trivial. There's no B field. But then you have the metric which is with one leg in the KK space and one leg in the base space is non-trivial to give you the A, right? So you have two not a Cartesian product of two complicated manifolds, but you have a very complicated product of two trivial manifolds.
So that's what I want to do, clarify in this example, is that's based purely for computational simplicity.
Right. Okay.
So it's like for this one that's this KQ reduction, like rigorously, fully, one can derive like expressions in lower dimension, maybe these kind of fields. So you will see like lower dimensional so which is 1 coupled to 5, for example, these kind of terms will be appear in the lower dimension. But if I want to compute some subset of those terms, which doesn't include this scalar term, I can simply say that's 0, and I do the computation. I still get like some subset of expressions it's not consistent, but it gives me a quicker way to do derivation.
I
And it's
see.
enough for me
I
to
see.
see some
Okay,
symmetry, consistency,
Right.
like
okay.
if there are any violation of ODD or not.
Well, what's the difference between A hat A and A hat?
So here I'm kind of sketchy because I didn't write down this external index. So in principle here you would see something and then
Okay.
and then here and then there. So this one is sort of different from that.
Good.
It depends how you do the indices.
Wait. You're not, oh,
So the scalars have two indices. What ODD scalars have two.
are they not primed, the indices?
Which one?
Are they not primed?
Which one?
The ones on A and A?
Here.
No, there's a prime index and that's contract.
Oh, that's the
so-
one that's contracted, okay,
So,
okay.
maybe
So these are on, okay,
yeah, maybe should be the sense.
sure, sure.
Okay, so the key point is like after sort of constructing this field terms, we now have like sort of single expression or two expression that's ODD violating. We know explicitly these are the ODD violating terms. So I'm starting with the hat and nothing. And now, so now one like to use this tool to fix like the effective action or like to study the effective action, one just need to write down everything like explicitly, like for example, and then like that's the flux. So this is 0 because it's this. So okay. So we define H flux as dV. And one can find out like explicitly just by computing this expression with the known data there. And find out it's 0. And the only stuff that we care about is something which is 1. So the only non-zero, so the only one. So these are the two non-zero components. So
You didn't really define what F is,
Yeah.
but I guess
okay, but yeah, sorry.
it's just the on
F
A.
is the H. So the only non-zero are these two. And here, okay, I'm sort of secretly saying these are sort of P-bar indices now. Like I can multiply P-bars here and there. So let's just pretend now somehow this is P-bar indices. But basically the point is that you see like there's a something with hat, something no hat. So if you see that's H squared, it will give us some something non-trivial with a hat F first. So that's the point. Like the explicit computation, one need to first properly define the field answers and then do all the stuff like kind of evolutionary. I mean, similarly for Riemann terms.
So why is there no F squared or F hat squared?
I think he's getting the violating terms.
Oh, yeah.
Oh, okay.
So here by this arrow, I mean, I don't care about violating terms
I
because
see.
what I
Okay.
really care is something that's violating. Because if one really want to write down a well-defined reduced theory, one has to first notify this. As I said, I'm here only the subset of something that's in the reduced degree.
Yeah.
But since I don't really care what's reduced degree doing, I don't want to consider those terms. So here my point is that we know there's some ODD value terms that's made of something that's hat, not hat. And I know this sort of give me tutors like what's the word? Like summation of two terms, one with hat, one without hat. So the product typically they will present something that's ODD value like f hat, hat. Right. And similarly, like one can so here I won't write down, but typically for Riemann tensors, they have like they want to begin with, so they will eventually get some terms with a hat, a becomes f hat, so it will contain something that's f or like some derivative happen something like that.
So if you said this, but the A will never appear on itself, only as F.
Yeah, because for gauge symmetry. Okay. Like you can do integration by parts to, like in the action you can sort of do some by parts and have some explicit A over there, but typically shouldn't be there.
Okay.
Can I ask something?
Yeah.
So can you take some other, reduced sector where you still preserve ODD by saying some combination of B and G will give you non-zero H terms, which do not have, all the non-zero H terms do not have F hat and kind of terms.
Sorry, can you repeat?
I mean, if you take some specific B and G,
Here.
yeah, can you then go ahead and say, well, there is a possibility to choose B and G such that you'll never have that kind of terms.
Let me see. So you mean if I change like these ansatz, so
Yeah.
this assumption, I'll get some new H. And it will give me some. So you're basically, is there a possibility if I choose this one such that there's no ODD value features?
Yeah.
Well, I don't think that's possible. Because like the point is that you only have sort of two ODD scalars to like you only have these two specific combinations to build some ODD scalar.
Okay.
And in general, if you do the compactification properly, then there will be some terms which maybe like ATA, let's say that, I don't know if there or not, but in general, the reduction is quite complicated, so it will give some like ODD value latent terms, which is not built from this kind of
Okay.
like this very specific way.
So this is the best possible case in which ODD could not be violated, and you're saying.
So to begin with, like ODD is not ODD is not okay. So in general KK reduction on the torus, there's no ODD, right? It only appears in this kind of string theories. So that means like in the general reduction process, you won't have some ODD stuff to begin with. So everything is kind of ODD evaluated in some sense. So and even here, like even we have some sort of way of making ODD scalar, we still in general reduction scheme, like there is some ODD evaluated term to be left over.
Okay. Okay.
Good.
Yeah.
More questions?
Is it clear? If I take scalar field theory,
Hmm?
scalar field theory on a torus, is there some ODD or not? Why is there no ODD?
I mean, scalar doesn't have, so you can say there's ODD and a trivially on scalar, but I can say any group just have trivially on scalar and it will be like nothing in some sense.
No, but I'm thinking like the spectrum has some kind of ODD symmetry. Like the momentum is such high dimensional momentum is a vector, so the ODD acts on that momentum, so there's some kind of or the symmetry in the spectrum.
In which spectrum, the reduced theory?
Yeah.
And you have some momentum modes? You
Sure.
said? Momentum modes of like with respect to internal indices or?
Right.
But I mean, a scalar.
There's only D of them, so you need two
Yeah.
to have something transforms in the.
Oh, there, oh,
You can sort of try to make like,
oh, okay,
like,
so there's an
example.
OD, not an OD. Yeah, okay, yeah, yeah. Mhm.
It is helping. Yeah, so any more questions or you think we're good? Alright, so, okay. Oh, yes, I'll just go through there. So typically the strategy to fix the, okay, maybe a sort of recap. We're saying we have so some effective field theory in 10 dimension, which is only, and we are only considering the three level string theory, so there's no genus correction, and this is made by just line corrections. And we are saying this one must reduce. Then minus D has sort of ODD symmetry. So that's the factor we wanted to use, right? And now, if I consider the two derivative order terms at this effective field theory made by NSX fields, so okay, so well, this one is actually we don't really care about that. So one can sort of say, okay, because diffeomorphism and other stuff, the two derivative term that we can construct in this action, in that action, is some Ricci scalar. And okay. Here I'll use sort of a torsion form Ricci scalar, which is defined by, which is derived by some torsion force spin connection, which is made by the common one, the ordinary one, the one that's made purely by metric. I forgot the name. Metric spin connection or functional Levi-Civita, I guess. So since this has three indices, that has three indices, you can sort of define some structure like that. You can use this, put in the Bertrand structure equation and find out torsion for Riemanns, and eventually you can find out what's the torsion for Ricci scalar. And for this, so once you have the explicit expressions of the torsion for Riemann components, you'll find out this one will reduce to, let's see. So it will only contribute, so one ODD violating term. From here, and from there, let's be right here. We can find that h squared in the higher dimension. This one will reduce down to something that's 6. So one can write down, like fine tune a specific combination in the higher dimensional theory. Let's say, I'll write it in the okay.
Don't do that.
So from there, one can. So that's. Let's see. Uh, well, that's the combination. That, I mean, from that analysis, we know this expression, once we do DD, we'll get like no dilated terms. And if one wants to write down the ordinary Riemann tensor, so no torsion Riemann tensor, or like a Ricci scalar, so since this is made by like a torsion pole spin connection that's defined with the H as the torsion part, it will like give some expression of like a Ricci scalar and H. After like doing that explicitly, one will find this is exactly the vectors.
Why was it useful to use the R minus? Why couldn't you just use R from the beginning and find this?
I mean, one can do that, but one will find out that if you define something with so Riemann functions,
Mhm.
you find that expressions will be easier, like it will be something with f hat, f or f squared. It's just for a convention, like in this case, you will give simpler like expressions.
Yeah, so there's no simple way of explaining why it becomes.
Yeah, like you can also define the other way, like I define with the minus one, but you can define the plus one.
Yeah, sure.
So there's no like one can do without this definition, but you need to do like maybe it's like harder to see like that kind of simple relation.
And the clause is equivalent. It's just your choice to take numbers.
Yeah, should be equivalent. I mean here we can just expand this in terms of the ordinary R and the H. There's nothing new. We're just compacting them in a better notation in some sense.
Now, I mean, you would do it with R instead of R minus, and you get a half F hat F.
Could be the case, but I haven't checked properly if I use R only. So this is just a term we know in the NSN sector. So there's the +4 dilaton term that we cannot fix it or derive it, since it doesn't really involve in our case, because it involve in our like ODD vector or this kind of structure. But anyway, we can still get some useful terms from this. I mean, it's quite trivial for the lowest order, but for higher orders, one can like find like quite a lot of subtleties. No more questions so far? All right, so now I'll give the next half of my example. And I'll just move this one. Well, that's the alpha prime term that's present in only string theory effective action or heterotopon. So now this time, so I just give you the basically the normal expression. In principle, one can start with a single term and then do the reduction and find some violating terms, and one can try to make some ansatz, like there should be some term like this, there should be some term like that, then do reduction and compare them and find out like this specific relative coefficient they can solve. But since today's talk is not meant to be like show how to fix this kind of Lagrangian or like this kind of action. So let's just use the known example, which is computed in these papers before. So, but in this case, one actually find out. So this whole expression, do the reduction, one will get some ODD violating terms with the proportional to so this one is the correct Lagrangian at the upper trial there. But once we do this reduction, we still get some ODD violating terms in the reduced theory. But all of these terms are proportional to lowest order equation motions. And one can then do the field redefinition to remove these terms by pushing them to the next perturbative order. So basically, these terms, we do field redefinitions are non-existent. So we can say, okay, there's the ODD. And here, but one might ask, is it possible to do some field redefinition to begin with instead of doing some field redefinition in the reduced theory, such that this new field redefined original theory directly gives us something that's ODD manifest. So something that's already just like in the lowest order case. In this case, we do reduction, we get ODD scalar like no violating terms. And it is actually possible. So one can add some. So if we add those two terms, so this means like the lowest order equation motion term for the metric, and similarly, this is the same term as that, and this means the lowest order equation motion for the medium.
And with this h squared with.
Yeah, so
with
this
only
one
two,
is-
or you contract two of them,
Yeah.
and one is left on.
Yeah,
So
so-
instead of that one, you contract one.
I see, okay, so the point is that for the result is that this trick with writing a 10D, just the change with equation to motion, you cannot do that for the third order.
Yeah. Yeah. So in this case, if I reduce this one instead,
And what is W?
W? Oh, W, that's omega, that's a speed connection. That's a speed connection with that. So minus one is the one that I defined before, and plus one is the just the other one.
Okay.
So, okay. So now for this one, if I reduce, I will just get 0. there's no like ODD validity terms for this specific one. But in principle, like it's not easy to find out these are the correct combination that you can put in such that once you reduce that, you won't get anything extra. But there are some systematic ways of knowing if there are such terms present or not, which is basically what I'm going to show next. So let's consider the same order, but this time we will leave the last term out. So this term, since we know that term will give nothing to the evaluating. Right, so this one has to give us something that's evaluating, which is so well, we already know the answer. Like, is there any possible that we can do some filter definition to begin with such that there's no such term either with this one? The answer is better, the last one of that. But suppose we don't know there's such possibility. What's the better way of like understanding or like calculating such that we know if it's possible to uplift or not? The uplift, I mean, basically if I have something term there that cancels this term. And the strategy is basically we consider this term and then we linearize the metric, basically just the metric. So this one, this is the equation motion for the metric. So it contains some like a Ricci tensor. This plus something. So this, more strictly speaking, is the beta function of the metric. If you do the single model of the string in the curve space line. So if we do some linearization of the metric, so then we can write this. So okay, after linearization, this will give us like a lot of things. So okay. So here for the Ricci tensor, once I do linearization, it will contain a bunch of like a partial H terms, where H is the linearized metric. There are things like three terms over there. I can pick one and start to realize that term. So I'll pick a specific term among those many terms in this expression. And the term that I'll be interested in is actually nothing to do with this term though, with the metric term. So I'll consider some term. So this one, this term one can also expand out as actually it's so I'll pick one specific combination from this, which is the full. So from this expression, there are many terms, and I can pick one term that I'm interested in, which is this term. So this term comes from some term from there and some multiplication to this. And now, our strategy is just to add like a sort of inverse term here, such that it will reproduce this term as I don't know. So here we also, so the benefit of doing linear version is that here we can only consider something that's has like we try to add something like H, E, or G, or like that. Basically, the buyout of like doing linear version is that we can add like simple ansatz instead of like doing using the linear version of the Riemann tensor or like Ricci tensors. So here, in order to cancel this term, we actually find out it's impossible to cancel this just using the linear metric and B field. It's because so here I'll need to break down the ansatz properly.
Yeah, very bad question, but what does it exactly mean to be linearizing the field bind metric, like field bind indices? Because these are field bind indices, right?
This ones.
Yeah,
Yeah, there are, but you can sort of be like so you can sort of be the other way, like since these expressions are provided, you can just change the indices to space time
and
indices.
the determining the session I would rather do in the normal space on the manifold, right? Rather than the facts, right? We need local data, right? That's my question.
Sorry, say it.
This HMU, the H, your.
Yeah, these are the space time indices. Yeah, these are space time indices. Oh, sorry. Yeah. So this is the original PDSs. So this one is changed basically. And this one is also basically the original PDS, but now I linearized. So if I have G, if I have not the fully linear metric, then that's A1 the same, A1 the same, and that's something that I set zero by assumption. And here I'll have something GMN plus A1, A1. But since A1 now we are taking them as something that's it will be something that in higher order, so we won't write down there.
Are you saying the assumption you had before, that G M prime was?
Oh shit, no, sorry. That's
Yeah.
delta. Right. So anyway, that key point is that that's the assets. So A1 are there, A2 are there. And now if I want to add some term in the 10-dimensional domain, let's say, because I want to cancel this kind of structure, this term. So E will be so A. So one attempt would be just okay. E and So one very naive attempt could be something like that, because what we are hoping is that once we do reduction, so basically setting up one to be internal. So let's say this is internal, this is internal. H will give us something like, so A1, and well, I don't know. So this is a combination of that's we have A plus minus. It will give us something that's a so that's what we expect, right? And then we might hope that this somehow will give this and it will cancel the reduced one. That's what we hope, but in this case, the answer to begin with is 0. Because that's a B field that's anti-symmetric, and we have something that's a product of, so that's symmetric. So it's a product between anti-symmetric and symmetric stuff. So that's 0. So that's not something that we can put as an answer, because otherwise we're just generating something out of 0. And so this answer is wrong. Let me try something like so okay, yeah. So here at HH use something that's symmetric pair that cancels with this. Let me try B, but it's the same. Still, it's that this term is the same as this term, so anti-symmetric translation is 0. So let me try to be HG or BH instead. But H is symmetrized and B is anti-symmetrized. These two indices are contracted with this, so they are 0. So using H, so using the metric and B field, you cannot write down something in the original theory that removes this term.
You cannot, for example, split the derivative for B, like a B squared B, put one derivative in front of the H's to make it non-identical.
But we want to remove these
Yeah,
terms.
you want to remove that term.
Okay.
Well, you can sort of say, try like if I do some total by parts, blah, blah, blah. Let's forget that. Yeah, so the highlight of this part is basically saying if you only metric and B field, it cannot cancel the term, which is something that we expect, right? Because I told you that the correct answer is made up by some spin connection, and spin connection is something defined by few lines instead of the metric. So actually, in this case, one needs to use well, now I guess it's linear ideal line. So this case, so very roughly speaking, that the other side. So this is the Riemann answer, which also reproduce this metric. So that's the common Toretto reduction Riemann constants. And here also, like due to like our sort of assumption that we don't really care about internal scalars, this is the delta function.
I don't get the indices here.
So that's the Riemann indices.
So on the upper row,
It's E and then A delta.
Which one?
yeah, so what is it, what are they?
So
A is, yeah,
A,
Prime,
One
oh, it's
prime,
not a
one
free
prime.
index,
no,
oh, it's some number,
yeah.
okay.
Yeah.
Yeah, it looks like it's 3 rows, or 3 columns.
okay, yeah, sorry. Yeah, so this is nonsense.
So, yeah, yeah.
now you can linearize vibines as well. Like doing something like what's it? Well, something that's let's go F. So I simply sort of assume this one as delta.
But what kind of delta is that? Doesn't look like a delta.
Sorry. Eta.
Why is it eta?
Because we want to linearize vibines as well.
Sure.
And you need to be eta to do to give the Lorentz. So you still want to. So
What is
you
an
want
eta? What is an eta within one index up and one index down?
Okay, here the indices are kind of weird. Yeah, I know. So maybe it's actually delta.
Yeah, it's that.
Yeah, could be delta.
Yeah, you don't need an eta because that sits outside.
That's true. Yeah, but the point is basically to extract one identity term out of it and add some perturbation. So the perturbation part is what we call F. And there are higher order F to make the expression consistent, but we don't care about that.
Yeah.
So basically, we can extract the linear vibine, let's call that, like this one. And now we can use this term. So this whole expression is, let's say, it's a bigger linearized vibine, so original dimension one, so that we can put.
So I guess you put in the thing you want to linearize that there is already a delta. Why is that delta not an E?
Which one?
Or because it's in the compact part and then you have a flat metric, so that's like something. Okay. So but it's secretly an E, and then you're also linearizing that.
Because because in our right, so what was the anyway, like it's either this or that the other way. Like this, so here we did some assumption here, right?
Right.
And that's reflected in this part.
Right.
Yes, the KTH in the sense.
Yeah. So now in terms of vibine terms, linear vibine terms, we can use this term to write down the ansatz. Let's say if I write down something that, right, I guess I will. But so the point is we want to cancel that term. So now we write something looks like all indices here are contracted. This term wouldn't be zero to begin with, unlike those previous terms. And this indeed, like this one is A1. So like after reduction, this one will give us something like A1, something that's A2, and this will give us
Sorry, question. Why did the first B have no index?
this thing.
Yeah.
Yeah, like these two indices are contracted,
Okay.
and internal indexes are contracted as well. So I'm just not writing since the even where they are since are, but to reduce this term, this term and that term, they are not
Okay.
I'm just not writing there. So the point is now this one now gives us something that's A1. This gives us something that's A2. And A1 times A2 is something like A hat plus or minus. It's either minus plus or plus minus.
Yes.
Anyway. And now, like actually this one, if you really look at how indices, you can sort of reorganize the indices so that you can add them together. Because that's something that's anti-symmetric, that's something also connected to antisymmetric, so you can put them into one single term. And this one will give us the exact structure that's just about. So that's the point. Questions? Because that's basically the main strategy that we're gonna use. So what we are saying that given sort of the already calculated or in calculation, we have some ODE violating terms that's proportional to the equation motion. In general, you can sort of try hard or just guess what are the correct like if you want to uplift, what are the correct structure that you can uplift, like this one, and there's one that has field by field line over there. Not field line. Spin connection. Like one can sort of guess or use other method to came out that term and find out this one reduce it reduce it to none. So it's ODD symmetry manifest. That's sort of the terminology I use. But if we don't know, like whether it's possible to do field redefinition to begin with, the strategy to find out if it's possible or not is by looking at those ODE violating equation motion terms. We linearize that, we pick one specific term and see if we can arrive some ansatz that can cancel this term. And making ansatz in terms of linearized fields is quite easy because you just pick the real fields and some fields. And in this case, in this example, we also find out that we also need some field lines, like it is possible to add more fields. So originally we thought we only need some metric and B field, but it's actually possible to put field line. Is that a metric? So that's the highlight of this part. All right, now we can go to alpha prime cubic story. Yes. Okay.
This is your current tool. That was your previous one.
That's true.
You're talking about the quadratic order.
No, I'll skip the quadratic order.
So that there the listing works at least.
Yeah,
The generalized level.
Yeah.
Do you know? Can you go beyond the generalized level with the uplifting?
Yeah, like
So you have the form. You have the formula accuracy.
yeah, like Linus computed like the exact expression in the second, like a second order prime. And in other like approach like W50, they also sort of so now because well in some sense we are really clear about theories like type 2 and type 2 that really correctly self-regulate. And so now we consider the cubic correction. So it has at least 4 Riemann terms. So the Riemann tensors from tensors, and plus like some combination of H of Riemann, and we don't care about relatives so far, so let's forget about that. But anyway, there is some expression that's made of 4 Riemanns applying cubic correction, and that explicit expression was computed by Linus as well. And by doing so, in the reduced theory, we will find out there are many like ODD violating terms that are proportional to equation motions. And let's pick one So there are quite a few, but one specific term, there's this term, which is violating, and that's the redefinition. And there are many others. And okay, one subtlety is that I actually find out that in this Lagrangian, like B fields only comes in pairs. So there's even numbers of B fields in the original theory. So there is a B parity symmetry. If I change B to minus B, the theory is still invariant. And this will be present in the reduced theory as well, because that's why I started with. So it should be there after I've done the reduction. In the original theory, B to minus, so it was B to minus B. And it is now translated to this high one, this low one. In minus B. And we're gonna use that because it still will help us to constrain what kind of asset we can have and what kind of terms to be present. So we inverse this term, it will give us many terms, and we only pick one subset of them. It will give us, so let's say we consider so here I'm using like A, B, C, D, I, J, K, whatever indices, but they are all just ordinary indices, they're the same kind. So my point is that given the known alpha prime unit correction term, Lagrange action, you do the Higgs reduction, sort of, you get some ODD validity term that's proportional to the equation motion. And to study if it's upliftable or not, we use our strategy, we linearize that, pick one term, like a reasonable term, which has the following structure. And there is secretly also its B-parity partner, in the sense that because this term alone is not sort of so because of B-parity, there is a similar term that has the similar structure, which is basically if I just flip this A hat there and with the plus or minus sign. So that's the term we're gonna consider. And in general, so one just do the same strategy there. We want to reproduce this part and sort of also taking care about the B-parity partner, because the term, the answer we begin with is also B-parity invariant, so it has to be like consistent with that as well. So one possible term is that we do So this is one possible answer that looks like we can remove this term. Like I keep this, since I'm doing the reduction, I only care about this part and the rest part they are basically have to be the same, otherwise there's no way to cancel them. And this one is one possibility, and the other one is if I change the order. And now I'm restricted back to just linear symmetry and B-field. And in this case, these are the only two possible answers that cancel this term. So to do this in like a general way, I can put some coefficient alpha, coefficient beta, and I do the reduction. For example, here I'm doing the contraction by A. I'm just simply putting this A hat A prime. This will give us A1 and A2 again, and the product is some A hat data. And one will find out, let's say this one has some coefficient, say 1. Then one find out if I say alpha, this is if I choose some specific alpha, specific beta, it will give me some overall coefficient and cancels that term. That's the strategy. However, in this case, our answers may generate other more like other ODG violation terms in general. Because if I add this term, so these two terms in the higher dimension, I can consider other possible contractions. For example, here this end contraction with this end contraction. So which is basically this and I do contraction here. This will give me some A hat A. It will give me some partial H, partial B, and blah 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 A hat A term. So by adding the answers, I'll also generate other evaluating terms in general. And one can just do the same strategy that, okay, if I add this two terms, this one is cancelled. If we generate new terms, I'll add more answers and to cancel them and repeat. But it's quite tedious to do like order by order. So one can actually find this in a more systematic way, just writing down one single most general answers to begin with, which is something like write the general answers and the partial, these partial differentiations are so that the field there are incorrect one-to-one indices with this term, because otherwise you cannot like cancel the term without different intensity indices. And x alpha is here h and then so for alpha it would be 1 over so that's the notation. So I can add like say so for that term, so for these two ansatz, they correspond to ansatz 1, 2, 3, and Q1, 1, 2. from these numbers, I know what are the field, like the fields over there. And the tensor structure is made specifically to cancel that term, so. These kind of coefficients is quite good enough just to track about what terms I'm considering. And also this has also sort of benefit because I know that I don't want to consider some answers that has odd number of B fields. So if I have like odd numbers of 2, then that means it's something that I shouldn't consider. So if I have 2, 2, 2, 2, that's 0. That's odd number in number 2. That's odd number in B fields. Or 2, 1. So, like in this case, we have like called alpha and beta, but in our most general answers, it's actually just we know there is C 1, 2, N2.
Okay, we have a question.
Yeah, go for it.
So your current procedure is to add a term like this and then find out the values of C so that you do not have additional terms that violate quantity from this, but also should have cancel the ones that you get for the place.
Sort of, but maybe you be clarified like by team. Sorry. Okay, so maybe I should do it. So basically, we want to consider that single term.
So you want to remove that, but at the same time not produce anything else.
Yeah, that's the point.
Okay.
So I can so these are the terms, 2 terms in the original baseline. I release down, they will give me something like 1 like this. So they give me that term, and since I know there is already a term there, so what the actual condition that I want is that 1 minus C1 2 1 1 2 plus C2 1 1 2 to be 0. That's the condition I require to cancel the term, right? And from these terms, that will generate other problematic terms, but so let's say
I'm sorry, which will generate this reduce will generate more problematic terms.
like the reduced one is already done, right? It cannot generate other terms. It's your answer that will generate other additional.
We can't just set these 2 factors to be such that just the equation is satisfied and other cease to 0. You can't do that.
No, like the point is that we need some sort of other C to be present, otherwise it will generate other terms. It's like this one C1 2 1 2, let's say, so let's say that's one that's 0, they satisfy this condition. This term also generates some problematic term, let's say
Okay.
H B partial H partial A hat partial squared A. And there's no way to cancel this one.
Okay.
And that's the point of us making a general answer so that we can add other C's
Okay.
to cancel this one.
Okay.
And one can like, so the point now is that one can actually see by B parity, sort of. So even in this case, because there's one B here, you need some sort of B there to make the answer. So it's like alpha 1, alpha 2, alpha 2. So equals to 2. So that's how we come out with the answers, right? Because we know the structure is like HHB, so we need 1, 1, 2. There has to be 1 to be the number 2. So these are the only extra relations. And we can do the same, like this one, because it will generate sort of from this contraction, you have the contraction, so it's the last few units. But we also want, so we want to keep the same structure here before, so we consider that two, let's say we keep the first one, 1, 3, 1, 1, 2. So that's something that we will generate. And so let's say, so in this case, it is gonna be so in this case it's called so now we generate from this contraction, and we can add the other C. We add this one, that contraction, to cancel this.
Okay.
But at the same time, this sort of term also generates this, right? And basically, in this process of generating and canceling, they give some strings, they give some conditions like, so for this one is T1, and
Do these have any deeper symmetry implications, or we just this is the one that works?
like it's not deep symmetry, it's just the well, they are sort of some consequence of B parity in some sense, because I have, so the general structure is that, general structure is that, like, if I have, let's say, two indices being constructed, and I know there's a 2 there, then this has to be 1, 2, or 2, 1. And they can, all these two terms contribute. They either cancel each other or they just do nothing.
Okay.
So after requiring everything to cancel out, you will find out the sort of conditions, and you replace that. So let's say this one is C1, 2, 1, 2. That's also C1, 1, 1. All right, so well, now you're thinking, like, it's basically, if you consider the contraction here, then the requirement is that 1, 2, something equal to you want something. You just split the 1, 2, and 2, 1. That's the dimension.
You said speaker.
Yep.
Go on, say. Yeah, you mentioned that you ODD is violated in alpha prime cube, but now you're saying.
No, I'm not saying it's violated. What I'm saying is that working will reduce down to some ODD violating terms, which are proportional to equation motion. And those terms which are proportional to equation motion, you can refill the definition to remove them out. in reduced theory.
Mhm.
But now the question is it possible to do a field definition to begin with in the 10-dimensional theory, such that this new field redefined 10-dimensional theory, you do the reduction, you won't get any of the inequality terms.
Okay, that you're saying is not possible,
Yeah, that I'm saying it's not possible.
based on the equations and constraints you get for C,
Mhm.
there is nothing that will satisfy.
Yeah.
Okay.
So here I listed like a few conditions to, the term regenerative cancel that, that's the required one. And you actually find out this one implies that this term is opposite to. So this term they are the same, they cancel. So in the left you have 1 and on the right you have 0. So that's inconsistent.
Mhm.
So basically, since that's already the most general answer,
Do they have to be real
real?
C's?
Actually, no, like it doesn't need to be real either. Here we are just lifting the identities in some sense. Like here, I'm not even thinking C as like a integer or rational, irrational, right? Like I don't care. Since they satisfy those conditions, these two have to be the same
Mhm.
and they cancel. That's 1 equal to 0.
Okay.
Basically, these 4 conditions, they have no like a.
Oh, you mean they should be same, right, not opposite? That's
Yeah, they're the
minus
same.
plus. Okay. Okay.
Yeah, so basically, now the point is that if I added the most general answers to begin with, and it shows that it will always be some ODD valid terms. So it is not possible that do some filter definition to begin with and generate something that's already ODD manifest. That's the result.
But you still can do field definition after doing these compactification and then.
Yeah. So
So-
it's not.
What does this imply?
Yeah, so.
Redefinition is the original theory now.
Mhm.
You can't add down on the original theory that will give you a reduced quantity manifestation.
So for example,
But it still means that you can have ODD as a reduced theory, right?
yeah,
You just have to put the definition there.
yeah,
So in this approach, what do you, what my question, okay, I'm failed to.
Not a redefinition.
Not, okay, okay.
so, okay, I guess you are asking like, what's the point, like, since I can.
What would be the implication
Yeah.
if you were able to?
Okay, if you're able to do it, then you can sort of formulate some ODD invariant theory to begin with.
That should be ODD in odd at all orders of occupancy, right?
Yeah,
Uh,
okay, so that's what we are only thinking here about occupancy for now.
So even if, okay, let's say that this works out, then would you say at alpha prime of 4 also you should have no ODD variety terms?
Meaning, so if I
Based
were,
on this answer, let's say it worked out.
but worked out, what do you mean?
Let's say you get a consistent equations for C. You can add a term in 10-dimensional theory, which gives you manifestly ODD terms at alpha prime 3. Would that have any implication for the higher orders of alpha prime?
You have to check like alpha prime with the 4 as well, because
Okay.
for example here, alpha prime 1 you check it worked out, doesn't imply like alpha prime.
Okay, okay.
Right, you have checked order by order. Although like in the higher order, there are possible terms that came from previous orders. Because by field definition, we are sort of pushing those problematic terms to the next order in some sense.
Okay.
Because once you do the field definition, like you are doing some field definition at all the alpha prime cubic and times another alpha prime cubic term, it will generate something that's alpha prime 6.
Yeah, okay, I can see what you mean.
Okay. So yeah, so in this case, we showed like using the metric and the field, there's no ansatz in the 10 dimension that you can do such that it will give you manifest ODE in your reduced theory. But as we see the alpha point case, we can return our field contents to like field by, blah. And now to do that, we simply just modify our general ansatz. So in this case, we only have alpha equal to 1, alpha equal to 2. And we know where's the now it's going to be expanded to linearized field line. Well, there's probably a part of so in this case, because you don't want to like change like the indices here, like what's the word? Like really troublesome in some sense. So you can. So okay. The few concept I want to consider is just the linear still one and B here, just like before in our prime case. But this one I can split into anti-symmetry symmetric part, and the symmetric part is actually just the metric in some sense, the linear symmetric. And there's some new field because by doing field lines, it's actually adding some sort of new stuff and new gauge symmetries as well. There's the anti-symmetric part, and so these are the fields that I'm considering to be in the ansatz. Now you have more like possible coefficients, and the condition is gonna be 1 plus like C1, 3, 1, 1, 2, or whatever. You know, like okay, here is my computer. I guess is digit, so I have no idea, but okay. So here actually, so okay. So let me call this number 1, this number 2 to be consistent with the one before. This number 3. So it's still 1, 2 there, 1, 2 there, and there's possible like 1, 2 again, 2, 1 again, and there's some C. It's plus minus, plus minus, plus minus, 2, 1, 2. Yeah, basically that's the condition that we want to consider. Analogous to this one.
Do you want your problem?
No, I'm fine. By now the analogy is already. I mean, it should be clear now. Basically, is that there's one contribution that came from the term that we want to cancel, and our answers just add a bunch of plus minus C, plus minus C, there. So that's one condition, right? And we also generate other terms, so we also get some like a bunch of like a C equations, and we'll find out actually these themselves is an identity if you want to satisfy it. So extra term being cancelled out implies this term to be 0 to begin with. So you always get 1 equal to 0 inconsistency. So either you say I want to satisfy this, but others there has to be one set of equation that's non-zero by the coefficient dimensions. So that's the way we sort of show there's no possible uplifter in the sense.
It's over constraint.
Yeah. And what we can do. So it's quite clear already that this already tells us there's no possible higher dimensional uplift that gives us manifest ODE. But one might say, yeah, what if I do weird, more extra fields? For example, in double field theory, there's like two field lines. So one can do that as well. So you sort of find two field lines, and in which one sort of begin A1, the other one gives you A2 in some sense, or like A or A hat. Basically, that, or like A or A hat. It's the same. So one gives you A, the other one gives you A hat only, but still you will eventually run with the same problem here. So for two field lines, doesn't work as well. You can try to do that like a three field lines, four field lines, but eventually the problem is that you always have a structure. And you can define like 100 fields, eventually to reduce down to a hat. So still, like there's no help that.
You're saying it confidently that no matter how many you add, it will
No, we
reduce
haven't
that?
shown, but
Okay.
we showed like at least for two field lines,
Okay.
it worked out. I mean, the extra field you add has to make sense eventually, right? Like for two field line, we can sort of make it sense.
But if you keep adding extra fields, would there be a manifestly free field or something that's more like a reductive field?
What do you mean by manifestly
I
free?
mean, like, if you.
Like, so you have to add like extra stuff to make some sense, right? Like here we can sort of add two extra stuff by taking a hat independently, in some sense. But the more stuff you add, like what's the symmetry goggles?
Yeah, that's my point. I mean, the more stuff you add doesn't necessarily mean you have more freedom to work with.
Yeah,
Essentially, you would always
so that's
like
the
same-
argument, right? Like the more stuff you add doesn't really have
Yeah.
the argument.
Right. So can I ask about your overall strategy? So you started with, when you do the election, you pinpoint one term you are trying to cancel, or like you are trying to find something that if uplifted would cancel that. And then you show it's impossible. Yeah, but what if you took more terms than one to try to cancel?
Yeah,
I mean,
so
this to me does not feel like a
yeah,
very general strategy.
yeah. So the good point is that there is only finite number of like ODT violating terms which are proportional to equation motion, and among those terms, let's say there are only 5 terms, and those 5 terms have very different tensor structure.
Yeah.
So each term is kind of independent from each other. Yeah, for example, if they are not independent, then this argument goes wrong, sometimes because let's say there's another term, the other equation motion term has similar tensor structure, tensor indices structure, then might be possible that something that you generate actually coincides with that term and they cancel themselves.
Yeah, okay, yeah.
But in this case, we are quite sure that those equation motion terms are very independent. They have very different tensor structures, so it's quite safe they just say, yeah, they're not that.
Yeah, okay.
Okay.
Is it possible that some total derivative or boundary we can add in that will cancel properly? Yes, sir.
So like you mean the 10-dimensional or like 10-dimensional, but so the total derivative you add in 10-dimension has to be sort of a total derivative in the reduced one, right? Because it's partial and let's say once you reduce, if it's internal, that's 0 to begin with, and if it's not, then you have something like this. If you're there, it can do something, but if I say my equation motion turns out none of them are total derivative, there's no point there. Like you cannot add this to cancel those terms. You can add this term to make something more complicated, but yeah. Right. So yeah, the result is in the 10-dimension. So basically you cannot uplift the field definition to original theory. So there is no theory that in 10 dimensions you reduce, you get ODD minus S theory. And this conflicts with double field theory, because double field theory is built with ODD symmetry to begin with. So if you reduce that, it will get some manifest ODD to begin with. So you conflict that and matches with your previous like abstraction. And also we believe it doesn't work out for generalized geometry kind of frameworks in 10 dimensions, because it needs the generalized metric to begin with, which is something that's already like I mean it's basically the same H there, which is 1. So yeah, that's our result.
It's kind
Done, I
of.
guess.
So about the answers you took for the compact metric, the B field is 0 and G is the identity. I mean, that makes complete sense now when you're just trying to find the violation, right? You're just trying to find an example that does not work, so you can take whatever answers you want.
Yeah.
But when you were talking before about the cases in which it worked, like alpha prime to the first, alpha prime squared, then that to me, it doesn't make sense to choose a specific metric.
So
That was just as an example, or did you also?
that's, I mean, that one can be fixed with this method. So the assumption of like an internal scalar in 0 is just for computation,
Yeah.
like make computation simpler. So it only gives some sort of necessary condition.
Okay.
That a consistent theory needs to be satisfied. So in principle, yeah, like for example, if there are some diatom shapes in higher derivative, for example, that one, we cannot capture it, right?
But if you want to show that, if there's a specific case in which this doesn't work, that means that the hypothesis of generalized geometry is not valid, right? You cannot use that for any case. If you're able to find a case for which you are unable to construct, unable to add a term which will manifestly give you already the entire compactification, that means you can say, okay, the generalized geometry will not give you all solutions, even if they find a very particular case in which it works perfectly fine.
So yeah, it's quite long to process, but let's say if somehow there is a way to do geometry of a prime cubic, then it will be different to this one.
But again,
But then-
it will never be the most general approach. It will only
Yeah.
work on very specific situations.
I mean, yeah,
Or you just provided a complex example, right? That
Yeah.
will definitely not work.
so it will not give the fully correct
Yeah.
answer, but maybe some subset could be correct. That's possible. But their approach to work like if you do in the reduced elements, in the reduced you do have ODD symmetry.
Yeah, okay.
It's just you cannot say that I start something that has ODD symmetry in 10 dimension and then I do reduction, it will give me manifest ODD symmetry.
Status figure again.
I like answering questions or doing this.